Now we're going to talk about the final complication for balancing, what happens in basic conditions. All right, so previously under acidic conditions, if we had just say a half reaction, say Br becoming BrO3 minus, we would add say some water to balance out the oxygens. Then we add the H plus to balance out the H. And so, your nuclei are all balanced now, but your charge isn't. So you add those electrons to balance the charge. So this is going to be our standard process for balancing in acidic conditions. And if we actually know we have basic conditions, we're actually going to start and go ahead and do this and then modify it. So we do go through the same process. We end up with that balanced reaction for acidic conditions. But then what we think about doing is, well, if this is in basic conditions, there are some hydroxides that are going to react with those H pluses. So what we do is we add enough hydroxides. Basically, you had 6 H pluses, so you're going to need 6 hydroxides, and you add them to both sides of the reaction. There's just going to be that many hydroxides present. And you know that the H plus and the hydroxide are going to react. You're going to get water from that process. So they're going to react. They're going to become water. Then you're going to cancel some of those waters because you're guaranteed to have water molecules on the other side. So you're going to have some redundant waters. You cancel out basically all 3 of these reactant waters would cancel out with 3 of the 6 product waters. So then you'd have something that looks like this. So you started with your balanced half reaction in acidic conditions. You end up with your balanced half reaction in basic conditions. You don't have to do it this way. I do it this way because I think it's easier. You can directly do it in basic conditions, but it's a little more of a pain. It's basically fewer, more difficult steps. I'd rather take the more easier steps to do some balancing. So let's look at an example. We want to balance the reaction in basic conditions. I have Cr2O7 2 minus reacting to become manganese 2 plus. That becomes MnO2 solid and chromium. So dichromate reacts with manganese 2 to make manganese 4 oxide and chromium 3. All right, so now we want to do the most complicated. We're going to balance in acidic conditions. I made this one nice and particularly difficult. So when we pair them up, manganese goes to manganese, chromium goes to chromium. We got all those oxygens. We don't want to be distracted by these oxygens being paired up. Oxygens are just going to be interacting with waters, all that kind of stuff. So what we're going to do is we're going to take each of those, deal with them one at a time. We're looking for our chromium. We'll do the chromium first. Cr2O7 2 minus. We're dealing with a lot. We're going to start dealing, and we're going to see, especially in this set of videos, a lot of kind of zany looking polyatomics like this thing. This is called dichromate. That's not super important what the name of it is. We just want to recognize that it's a chromium and a chromium, and that's what's really changing. So the first thing is to balance the atoms. Do 2. Got that right there. So the chromiums are balanced. Now we need to balance the oxygens. I guess we can use some phases. That's a liquid. So even though it's in basic conditions, I'm going to follow the process for acidic conditions. So the 7 times 2 is 14 H plus. So I'm just going to work my way through the acidic conditions, and then we'll deal with basic at the end. We're going to combine everything. So now I need to add electrons. So when I look here, I got 14 plus. Let's write these out. So I kind of got big numbers. 5 plus 14 minus 2, and then 2 times plus 3. So that's positive 6. 14 minus 2, that's positive 12. Positive 6. So I need some electrons over here. And I think I need 6 of them. That'll make up for it. So my chromium is balanced. Now I'm going to do my manganese, the NMN. So in that case, I get Mn2 plus aqueous with MnO2 solid. So the MNs are balanced, but the O's are not. So I got 2 O's. I'm going to need 2 waters. Then I asked to count for that with hydrogens. Double what I added there for H plus aqueous. So if I look here, plus 2 plus 4, I need more electrons on the positive side. So that'd be plus 2 electrons. So I can see it's a good thing. I have electrons on a reactant side, electrons on a product side. This is my oxidation step. That's my reduction step, so that's good. See, everything checks out. Everything makes sense. We want them on both sides, so that way they'll cancel out. We do need them to be the same amount. 2 needs, and I got 6, so I need to multiply this by 3. I'm going to do 3 times the entire manganese one. So that would be 3 times 2 H2O liquid plus Mn2 plus aqueous becomes MnO2 solid. So I got the 6 H2Os plus 3 Mn2 plus becomes 3 MnO2 plus 12 H plus 6 electrons. So now these electrons match to this. So I've got this one, I've got the numbers balanced out. I need to add them all together now. Do that right here. Actually, we're going to move to a second page to do that. So I got my reduction step right here. Chromium, 6 electrons plus 14 H plus the Cr2O7 2 minus becomes 2 Cr3 plus aqueous plus 7 H2O liquid. Just copying over my previously balanced reactions. 6 electrons canceled out. So add them together. 14 H plus Cr2O7 2 minus plus 6 H2O liquid plus 3 Mn2 plus aqueous becomes Cr3 plus the 7 H2O liquid plus 3 MnO2 solid plus 12 H plus aqueous. So pretty busy because we do have, a lot of waters and H pluses in both of them, and those need to combine together and eventually cancel. So now that they all combine together, we do want to cancel some out because I got 14 H plus becoming 12 H plus. So the 12 H plus should cancel out. The 14 will become 2. Similarly, these 6 waters entirely go away, and this 7 becomes a 1. So now that's going to clean it up quite a bit. It's going to look more the size we're used to. 2H plus aqueous plus Cr2O7 2 minus aqueous plus 3Mn2 plus aqueous becomes 2Cr3 plus H2O liquid plus 3 MnO2 solid. So this right here would be done and balanced for acidic conditions, but dealing with basic conditions. So if it's basic conditions, that means there's not a lot of H pluses floating around, right? There's not those are not present in a basic solution. Instead, there are hydroxides around. And we know that what would happen is there would basically be hydroxides that would react with that. And so we add hydroxides to both sides based on the number of H pluses. Okay, so once we have the balanced acidic, we just add hydroxides to it. And so what'll happen is these together will react to create water. We know hydroxide and H plus, you combine those together, you're going to get some water. So this would be 2 H2O liquid plus the Cr2O7 2 minus aqueous plus 3Mn2 plus aqueous becomes 2 Cr3 plus aqueous plus the H2O as a liquid plus 3MnO2 solid plus your 2 hydroxides. And so the thing is now, again, just like we had to cancel here, you can see this one water will cancel out with one of those, giving you one water up there. So finally, we can get our answer. It is H2O liquid plus Cr2O7 2 minus aqueous plus 3Mn2 plus aqueous becomes 2 Cr3 plus aqueous plus, no more waters, 3MnO2 solid plus my 2 hydroxides. That is the balanced redox reaction for basic conditions. So the reason why this one took so long and was so complicated is because we had all those oxygens, right? That basically both sides had oxygens we had to deal with. And so whenever you have this situation, each half reaction takes longer. Then you need to do some cancellation. Then, so that makes it longer. Then we need to do the base. This is about as complicated as these will get. They do not really get much more complicated than this because this was as many oxygens as possible. You had the basic thing you had to deal with. So it's really complicated, but in this regard, there's not too much more you can do that you can make it complicated. You don't have to necessarily, there's a way you can just do it straight in basic. I prefer to use the acidic balancing and then put it into basic conditions, just drop these OHs and change it that way, as it's just a little cleaner, especially when you're adding the oxygen and the hydrogens. It's less likely you'll make a mistake there. But we can always end up with our answer. You know, those hydrogens and oxygens, their oxidation number isn't changing. It's just H is +1, O is -2. So they're not participating. They're not really spectators. They are participating in the chemistry of forming compounds, but they're not transferring electrons. So they're just kind of there to keep everything overall balanced and kind of stable in compounds or whatever polyatomics you're making. We can balance any redox reaction we want to now.
That's it. Participation 11.4 has 2 questions. You want to find both of them, get them answered, get those answers submitted over on Blackboard by Tuesday evening. We got the midweek 7 homework due Wednesday, and covering this set of videos, start of chapter 17 here. And then chapter 15 to 16 participation follow-up will be Wednesday at the start of lab, and then we'll go from there to do the redox titration lab. Again, the redox titration, that's a topic in the second set of videos. So when you're doing the pre-lab, if it doesn't, I don't expect you to necessarily be super familiar with the technique. We'll go over it in the videos. You'll see it in lab. So hopefully the videos, second set of videos, will be a bit more meaningful because you've already seen all this stuff. But we'll do that. And then if you have any, and then when the post-lab is around, I will expect you to know a bit more about how it works. But that is going to do it for this set of videos. There's the participation answers. We'll go live Tuesday. We'll have another set of videos later this week where we'll talk about redox titration. If you have any questions about anything, let me know. Otherwise, enjoy the rest of your day. I'll see you for the participation follow-up 11 a.m. in room 230. Bye-bye.